Hey all, welcome back to Notes with Griff. This is 6.8, Relationships Involving Delta H Reaction. So we're going to start off with just how to manipulate delta H. If you recall in 6.7, we talked about delta H just a little bit with our calorimetry. So we're going to just keep expanding on that, and the next two sections actually help us go really in depth with delta H. So let's just jump right in here. So manipulating delta H of reactions. So first off, if a chemical reaction is multiplied by some factor, then delta H is also multiplied by that same factor. Why do you think that is? As you recall, all along we have talked about delta H being an extensive property. And hopefully by this point we know that an extensive property means it matters how much we have. And you can think of it in these terms. If I have 2 gallons of gas, I can go further than if I have 1 gallon of gas. So let's take a look at an example down here using chemical reactions. So our example, our generic reaction is A plus 2B gives me C. And so that equals some delta H value, and we're going to call that delta H1. So if we double our coefficients, or these big numbers out front, that means delta H will be 2 times that H1, which makes sense because we said that delta H is an extensive property. So if we double it, we're going to double the output, if you will. Our second statement says, if a chemical equation is reversed, then delta H changes signs. So let's take a second to think about that one. Why do you think that is, that if delta H changes, if we flip the reaction, delta H changes signs? Anybody thoughts? Well, if you cheated and kind of looked down at this example down here, that's not cheating, that's using your resources wisely. But we've got A plus 2B going to C. Then if we flip it, we get C going to 2A plus B. That makes sense because if we're going in the forward direction, we've got a delta H. But if we go back that same exact direction, delta H will just be the opposite of that. It's kind of like Newton's laws of physics where we have, for every action, there's an equal and opposite reaction. And so we're talking about it in those terms. All right. So if we flip a reaction, we flip the sign. Our third one is the one that's most useful. And we actually use those top 2 statements to do the third one. And the third one says, if a chemical equation can be expressed as a sum of a series of steps, then delta H for the overall equation equals the sums of the heats of reactions for each step. This has its own specific name, and that's called Hess's law. Hess's law basically is the law of summation. In fact, in some chemistry books you will see that. Law of summation. So our law of summation basically says that the steps add up to be the total. Which is awesome. Our steps add up to be the total. That seems like something we can handle. So let's check out this example down here. We've got our generic equation that we've been using all along. A plus 2B equals some delta H1. Then we have added another reaction that says C equals or goes to 2D. So when we do that, if you look, the C's cancel. So it's just like thinking A plus 2B goes to 2D. And so delta H3 there would equal delta H1 plus delta H2. Let's look at this in terms of a potential energy diagram. This is called a potential energy diagram, and we'll talk more about those later, but they will become more important as we move through our our thermodynamics knowledge. So potential energy diagram. If we see here, here's our first reaction. A plus 2B goes to C. So as we see, our energy goes up there to delta C, or 2C. All right. Then we have our C going to 2D. And that, if you can tell, that looks like it's going in the opposite direction, like the energy is going down, and this one, the energy is going up. So in this case, they're kind of working against each other, but it's still a summation because if delta H2 is a negative sign, then we're just subtracting the two. But in terms, our delta H is just the sum of those two reactions, because it's really the difference in those two reactions. But if we had them each going up, obviously our difference, right, our difference here would be that total, which also makes sense. All right, so let's see if we can't put this into practice. So here's our example, Hess's Law example 6.9. So our goal is to find the delta H for this reaction here. 3C plus 4H2 gives us C3H8. And we're going to manipulate these equations right here to get to this equation up here. So let's jump right in. What I like to do when I look at these equations is I try to find, it's kind of like a puzzle. You're trying to put it together so it all works out. If we look in this first equation here, this is the one I'm currently looking at, we're trying to figure out what in this equation matches up with that top equation. And as you can see, it's the C3H8. But unfortunately, there's a problem. C3H8 is a reactant here, and in the reaction, it's a product. So we need to flip the reaction. So when I do this, I'm going to erase that real quickly. When I do this, I'm going to multiply this whole reaction by -1. That tells me that I'm flipping it. So we're going to leave our state symbols on. So I'm going to flip it, and so I'm going to have 3CO2 gas plus 4H2O gas yields C3H8, which is now on the correct side. We wanted it as a product, gas, plus 5O2 gas. And so our delta H, we also have to manipulate. We flipped it, so we're going to just change the sign from a negative to a positive 2043. All right, let's check out that second equation. The second equation, right here, we're trying to get something that matches up top. And if you can see, the very first thing matches up. We've got C up there. Except in this one, we only have one C. So if I multiply this whole reaction by 3, that'll give me the 3 C's that I have in the reaction I'm trying to get to. So if we throw it on there, 3C solid plus 3O2 gas, arrow, we get 3CO2 gas. So again, we have to manipulate our delta H, and that's going to be 3 times negative 393.5, which comes out to be negative 1,180.5. All right, let's do the third equation. Take a couple of seconds while I'm flipping colors here. This equation, what matches up in that top equation? And so what are we going to multiply it by? If you said 2, you are correct. Ah, man. I don't know what's going on there. All right, so I'll put that out there. There. I'm going to multiply this whole reaction by 2, which is going to give me 4H2 gas plus 2H2 gas. How about O2? All right, arrow, and then we get 4 waters, H2O gas. And again, with delta H, we have to manipulate. We have to multiply that one by 2, so we're going to take, let's not put the negative sign just yet. We're going to take 2 times negative 483.6, and that's going to give us negative 967.2. So now let's just check and make sure we've done this correctly. This is kind of the math version of doing things correctly. So we're going to just add this up and make sure that this reaction, these 3 reactions, add up to this reaction up on top. So if we look there, as we're looking through the reaction, I have 3 CO2s here and I have 3 CO2s there. In math, if I have 2 like terms but on opposite sides, they're going to cancel out. That's going to happen in chemistry as well. All right, so moving on. 4 H2s, H2Os, and 4 H2Os down there. So those cancel. C3H8 is something I want, so I'm going to leave that there. Let's move on to this next one, or this last one. We've got 5 H2Os on the product side, and down here there's 3 here, and there's 2 there, so 2 plus 3 is 5, and that cancels out. All right, so let's write what we have left and see if we did a good job. So we got 3C solid plus 4 H2 gases gives us C3H8 gas. And that does match up with the equation we were going for. So now we can just add these delta H's up here and see what we get. Delta H is going to come out to be negative 104.7. But if we check sig figs, when we're adding and subtracting sig figs, we keep the least number of decimals. Well, this one's accurate to the tens place. This one's accurate to the tenths, and that one's accurate to the tenths. So our answer can only be accurate to the tens place, so that's negative 105, and our label is kilojoules. And there is our answer. And we are done. Great work. See you next time.